Hello, this is Dr. Chen, and this is the lecture for Chapter 5, where we'll be talking about different ways of transforming your raw scores into versions of your scores that would be able to give people tons of information about what that score basically means. So, let's get started. Um, oops, I need to There you go. That makes a little bit more sense. So let's start out with the basics. So a raw score is the score that you observe, or the untransformed score, before any operation is performed on it. And raw scores basically form the basis for other scores, such as percentiles, standard scores, and so on. We'll talk about those things in just a little bit, because those transformed versions of your scores are important for being able to give any particular meaning or interpretation as to what those scores mean. Raw scores by themselves are quite meaningless. So, for example, if you know that someone got 18 out of 20 questions correct, we still have no idea about how difficult the questions are or what types of questions were used. Um, how did that person do compared to others? And just a bunch of other information that would help us make sense of that particular score. So for the quiz, definitely study and know why we need to transform raw scores, because basically raw scores don't give us a lot of information at all. So take a look at this example in table 5.1. We can see that Stu, which he is right here, Stu with ID number 36 got a raw score of 18, and Lori with an ID of 25 right here at the bottom got a raw score of 7. And we know that there are 20 items on the test, but we don't know a whole lot more. Um, uh, this is a big disadvantage because in some instances, a low score may be better, but in other instances, a high score may be better. So you need to transform those scores to make sense of them. So to help in interpretation, we need to talk about two general classes of scores. Norm reference scores, when we use norms to evaluate one's relative performance, and criterion reference scores. We'll spend the majority of this lecture talking about norm reference scores, actually. So within norm reference scores, within this category right here, we'll discuss scores such as percentiles, deciles, stanines, standard scores such as z-scores and t-scores. Um, so a norm reference score, for example, would be able to tell us that maybe Stu scored much better than the majority of the other 49 test takers in that example. Um, when it comes to criterion reference scores, we are comparing the scores to an absolute criterion, and that absolute criterion it depends on what is that external criterion that determines what is the absolute performance that this person needs in order to pass this particular test. So, for example, if we decide based on some external information that a person needs to score 95% and above in order to pass, that itself is going to be a criterion reference score, because it doesn't really matter how Stu did compared to all the other test takers. As long as he made it above 95%, that's all we care about. So in terms of the exam or for the test, now we know the difference between norm reference scores and criterion reference scores. Let's talk about norm reference scores. Norms are a set of scores that represent a collection of individual performances and is developed by administering a test to a large group of test takers. This complete set of scores then is the measure by which an individual score is compared to other test takers. There are various ways of calculating norm reference scores. We'll talk about percentile ranks, Stanine scores, Z scores, or T scores. We'll talk about deciles as well, which is kind of like a form of percentile ranks, except you're dividing it by a different denominator. Let's talk about percentile ranks first. A percentile rank is essentially a point in the distribution of scores below which a given percentage of scores fall. So, For example, the 45th percentile, this is the score below which 45% of the other scores fall. In general, the lower the percentile, the lower a person's rank within that group. This is good information to know, but also keep in mind that this definition doesn't really tell us anything about absolute performance. It's just relative. It's relative to all of the other people that took the test as well. So know what a percentile rank is, how to interpret it, what information it gives us, and what information it doesn't give us. So how do you calculate a percentile rank of a person's score? So first, what you want to do is you take that table that I had just showed you before, and you want to rank all the scores in an either increasing or decreasing manner, with the lowest score, lowest value at the bottom of the ranking. Once you rank all those scores, then second, you want to count the number of occurrences where the score is worse than that particular person's score, that person of interest, that is. And that will be B, essentially, the number of observations with the lower values divided by the total number of observations in that table. You multiply that by 100, and ta-da, you get the percentile rank. So this table right here shows the scores that are ranked by descending order, starting with the highest score, going down all the way to the lowest score. This is just a continuation of that. And we can see over here to calculate where is Stu. Where are you, Stu? There you go, right here. It's bolded here. So to calculate Stu's percentile, you want to count the number of occurrences where the score is worse than Stu. So in total, if you were to count the number of people below him, it's 41. 41 scores of people that are worse than Stu. And the total number of scores is 50, so you take 41 divided by 50 times 100. Stu's percentile rank is an 82. That basically means that Stu did better than 82% of the other individuals in the group. So what's really nice about percentiles is that they are very easy to compute, easy to understand, and can be applied to almost any test situation. Not so wonderful side of percentile ranks is that the difference in terms of performance between percentile ranks towards the middle of the distribution right here, and this is what we call a normal bell-shaped distribution. We're assuming that the test scores given a large enough sample is going to approximate a normal shape curve where most of the scores are going to be most frequent around the mean, the average of that entire distribution. So anyways, I was saying the not so wonderful side of percentile ranks is that the difference in performance between percentile ranks in the middle of the distribution, so around this area. So let's say we are comparing the percentile ranks, the 50th percentile rank and the 60th percentile rank. The difference in performance between those two percentile ranks is quite a bit different compared to comparing, say, the difference between the 90th percentile rank and the 99th percentile rank, which is approximately 10 percentile ranks right there. And so the intervals are not really equal, and the absolute performance of a person who got a where's my cursor right here? Who got a 95th percentile rank, versus a 99 percentile rank. So the person who is at the 99 percentile rank arguably is a lot better compared to someone who's at a 95 versus 90. Someone who's at a 60th percentile rank compared to the 50th percentile rank, not a whole lot of difference right here. That's probably one disadvantage of interpreting percentile ranks. Couple of other common language that statisticians use to convey the position of a person on this normal distribution. The 50th percentile is a lot of times referred to as the median. The 25th percentile, which is somewhere around right here, is what we call the first quartile, or Q1. And then the 75th percentile, which is around right here, is called the third quartile or Q3. So you'll probably run across these terms uh, whenever you hear people wanting to describe certain portions of their distribution. This is really important for you to know for the exam as well. So just take note of this. Make sure you know what Q1 and Q3 and the median basically represent. So as you already know, or you can probably guess, a percentile is 1 out of 100 parts of an entire set of scores. That's why it ranges from 1 to essentially 99. Therefore, if you took a set of scores and divided it into 10 equal parts rather than 100, you then have a set of deciles. The first decile is the first percentile ranks. The second decile is the second set of 10, and so on and so forth. So this table here presents a summary of these different measures of percentiles: percentile, quartile, and decile. I just realized I didn't talk too much about what a quartile is. If we go back again to this table here, so the quartile is going to be any area between 0 and the 25th percentile. So 0 and the 25th percentile is going to be in the first quartile. Any score that's between the 25th and 50th percentile, 25th and 50th percentile, that's going to be in the second quartile. Any score between the 50th and 75th percentile, that is the third quartile. And any score between the 75th and 99, that's going to be in the fourth quartile. So if you come back again to this, you see that right here. From the first percentile to the 25th, you got the first quartile, and deciles are basically intervals of tens right here. And you see going down the list. So in this example, Stu's score, his raw score is an 18, is at the 82nd percentile, the fourth quartile, and the 9th decile. Alright, let's talk about a different type of norm score, still kind of based on the percentile ranks, but not really, just a different way of chopping up the distribution. Stanines are a particularly interesting type of norm score. They're interesting because just like percentiles, they do divide the distribution into segments, but unlike percentiles or quartiles or deciles, Stanines divide the distribution into 9 equal segments. And to make things a little bit more comparable across the segments, each of the 9 Stanines represent 1/2 of a standard deviation. Except for Stanines 1 and 9, which are just a little bit smaller, but pretty much everyone else is about 1/2 of a standard deviation. So Stanines are useful for a couple of reasons. They're easy to compute, they're represented by a single digit, which communicates lots of information easily and effectively. Stanines also represent equal units along the continuum. So Stanine 3 and Stanine 6, for example, each represents a half standard deviation of scores. And unlike percentiles, raw scores equivalents of Stanines are not disproportionate along the scale that is being measured. So as you can see over here, this table shows how Stanines relate to percentiles, quartiles, and deciles. In this example, Stu, who is in the 82nd percentile, is in the 8th Stanine. Okay. Our next type of normative score involves those that are often referred to as standard scores. A standard score is one that is standardized based on a certain metric. In the case of z-scores and t-scores, and this is important for you to note, the metric is the standard deviation, which when we look at the formula, that's going to make a lot of sense. So what is the standard deviation? The appendix of your textbook is going to talk a little bit more about that, but it's basically a measure of variability within a set of scores. Standard scores are very useful because they allow us to compare the relative standing of that person in that distribution and across distributions as well. So that's really cool. Compared to percentiles, you get two different exams, and if you were to standardize those scores and make them into z-scores, you can essentially compare those scores even though they came from totally different exams, different formatting, measuring the same thing. So z-scores allow for comparison across different distributions, which is a huge advantage. A z-score, so how do you calculate it? A z-score is the result of dividing that amount. You take the person score minus the mean or the average of the set of test scores, and you divide that by the distribution of the standard deviation. So for example, if Stu had a raw score of 18, and let's say the standard deviation for the set of test scores that we've been working with is 5, so S is going to be 5, and let's say the mean is 13. So it's going to be 18 minus 13 divided by 5, which equals to 1. So z-score for Stu is 1. Great, but what does that mean? Well, we know that z-scores, and this is important for you to know too, z-scores have a mean of 0. So the middle of the distribution is a 0. And any scores above the mean of that distribution is going to be positive. And any scores below the mean of the distribution is going to be negative. We also know that a z-score of 1 equals to 1 standard deviation above the mean. A z-score of 2 equals to 2 standard deviations above the mean. And you see that same pattern for any scores that below the mean too, because a normal distribution is symmetrical. So in other words, a z-score is simply the number of standard deviations away from the mean. So that immediately should give you a very good idea about where a person stands in that distribution just by knowing the z-scores. So as shown here, a score of 1, which is pretty much equivalent to a z-score. A score of 1 corresponds to the 84th percentile. A score of 2, say you got 2 in terms of a z-score, corresponds to the 97th percentile. My cursor is not moving. There you go. 97th percentile. And a standard deviation of 3 or a z-score of 3 corresponds to the 99th percentile. So if you can imagine this pattern of distribution in your mind, knowing the z-score of that person should automatically let you know what the percentile rank of that person is, or at least a rough idea about where the person stands in the grand scheme of things. In this table, you can see the z-scores that are associated with each of the raw scores using that formula that we just talked about. And it's just nicely calculated for you. So we can see over here that Stu, it's a z-score of 1. That puts him at about 1, that puts him at the 68, I believe, 68 percentile. Is that right? No, sorry, 84 percentile in that distribution. Okay. A normalized standard score, it's pretty much what a z-score is when it's forced into a distribution that has characteristics of a normal curve. Typically, when people talk about z-scores, the assumption is that it's you can kind of interpret it similar to it being in a normal curve, just like what we've been talking about. Let's talk about a t-score. So while z-scores do give you a ton of information, one of the disadvantages of z-scores is it has less than outstanding values placed on any negative score, and sometimes people don't like to receive a negative sign in their scores. It just makes them feel bad. So if you don't want to give your students or the people who are taking your test a negative score, you can give them a t-score. A t-score is basically a variant of a z-score as shown in this formula over here. you take the z-score, multiply that by 10 plus 50. So if for Stu, his raw score was an 18, which is equal to a z-score of 1. So you get 1 times 10, which is 10 plus 50. So Stu's t-score is a 60. So you may realize immediately that this this alternative way of calculating the standard score eliminates any negative number, and it eliminates any fractional scores. So that's pretty cool. So know what the mean and standard deviation is for the z-score. The mean is 50. The middle of the distribution is always going to be a 50, and a standard deviation is a 10. So this is that same table, except now we've converted the z-scores into t-scores. So, oops, Stu around here. I guess I don't. Again, Stu score. His t-score is a 60, which is 1 standard deviation above the mean. So I mentioned before that t-scores eliminates any need for any negative numbers. So obviously any negative z-scores are now transformed into positive t-scores. You'll also notice that we no longer have any decimal points, because they're all when you transform it, there is no need for decimals anymore to convey the same type of information. So all of what we've discussed so far are forms of norm-based scores. An alternative to norm-based scores are criterion-based scores or criterion-referenced tests, where there is a predefined level of performance used to evaluate outcomes, and it has nothing to do with the relative ranking among a distribution of scores. The importance of criterion reference scores cannot be understated or overstated. We expect people to do thousands of things that are based on an absolute scale of success. So we expect police officers, for example, to know the rules of law enforcement, not just 50%. We expect new nurses to be able to start an intravenous line with a 100% level of success, not just better than their classmates. We expect school bus drivers to drive with few miscalculations, not just be better than their friends. So the key to any criterion reference test is to figure out what is that predefined level of performance. That's probably going to be based on some type of external criteria determined by the experts of the field that decides what is the absolute performance that needs to be demonstrated in order for this person to pass the test. Now, the last thing that we'll cover in this chapter is the standard error of measurement. So you may recall from chapter 3 on reliability that there are all kinds of influences that can affect the validity of a score. The standard error of measurement is a very simple measure that gives you a sense of how much the test score varies for an individual from time to time or from test to test. So in other words, it gives us a measure of variability we can expect to have around an individual's test score, assuming that person goes through repeated testing. So how do we calculate what the standard error of measurement is? This is the formula. The standard error measurement is basically a function of the standard deviation of the test score, so that's S over here. Multiply that by the square root of 1 minus the reliability of the test. So we're taking into consideration the reliability as well to figure out what is the amount of variation we can expect given the reliability of the test. For example, for the example that we've used throughout the chapter, let's just say that distributional scores that we've been talking about, the standard deviation is 5, and the reliability of the test is, let's say, 0.87. Remember that reliability can range from 0 to 1, so 0.87, that's fairly good. If you plug in those numbers, 5 into standard deviation, my cursor is not moving again. There you go. 5 into standard deviation, 1 minus reliability, which is 0.87. You crunch those numbers, you get an SEM value of 1.8. So what does that mean? Well, what do we know about normal curves and the distribution of scores can also be applied to SEM. So for example, Stu got a score of 18. That was his raw score. Now we also know based on our calculation that the standard error measurement is 1.8. This can be interpreted to mean that we can be 68% confident. Now why 68%? If you take 84% minus 15.9%, it's about 68% over here. We can be 68% that his true score is going to fall within plus minus 1 standard deviation. Plus minus 1 standard deviation. Which basically we're in terms of SEM, we're going to replace standard deviation with the standard error, the mean. So it's going to be 18 plus minus 1.8. That's going to give you a range of scores of between 16.2 and 19.8, assuming the test scores are normally distributed, of course. So 68% of the test scores are always going to be within 1 standard deviation from whatever that estimate is. We can also be 95% confident, that is two standard deviations right here. So that's 97 minus 2, that's about 95%. We can always be 95% confident that his true score will fall within 18 plus minus 1.8 times 2, which is 3.6. So if you take 18 minus 3.6, that's 14.4. 18 plus 3.6, that's 21.6. So we can be 95% confident that his score, his true score, is between 14.4 and 21.6. And that's based on the best estimate that we got, which was an 18. One thing that I want to bring your attention to in regards to the SEM formula is as your reliability goes down, your SEM value is going to go up. So what does that tell us? Basically, you would want to use a reliable test, because when you increase this goes down. Our goal is always to reduce the size of the standard error measurement to make the test a more accurate measure of what we intend to assess. So that's why it's really important for you to use a reliable test, so we can narrow that window and have more confidence of what our true score is. So in summary, there are lots of ways to define and interpret the performance of a test or the score of a test. Each of these types of scores that we just talked about, they all have its role in the interpretation of test scores. Know how to calculate them, the pros and cons of each, what can we conclude from each type of information, especially when they relate to one another, like how Z scores are related to T scores and how Z and T scores can be related to percentile ranks, all those good stuff. So know how to calculate them, know the pros and cons, and what we can conclude from each type of information. All right, so this past, I guess, about 5 weeks, we've been discussing a lot of what kind of falls under the large umbrella of classical test theory. Next week, we're going to venture a little bit into what is now called modern test theory. So stay tuned for that.